கொஞ்சம் முன்னாடி வைக்கணும். அப்புறம் வைக்கல. நான் இப்படி இங்கே க்ராஸ் பண்ணேன். இங்கே நோக்கி நோக்கி வந்து ஓகே ஓகே தலை வச்சாரு என்ன கட்டாது உங்களுக்கு ஓகே ஒன்று ஓகே 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 சார் சொல்லுங்கள். இப்போ இல்லை, ஸ்பீக்கர் பேசும்போது இருக்காது.
I request all participants, please take your seat. We will start after a couple of minutes, please. Respected dignitaries, distinguished speakers from the industry, our valued patrons and sponsors, fellow TEF members, ladies and gentlemen, good evening to one and all. It's a pleasure to welcome you to the second technical seminar of TEF 2026. Your presence today underscores the spirit of collaboration that defines the TEF community. Your ongoing participation and support over the years have been instrumental to our journey, and we are grateful for your continued association. We are honored to host a distinguished audience of experts, practitioners and learners, all connected by a shared commitment to technology and innovation. Let us make today's program impactful and inspiring. To begin our proceedings, on traditional and auspicious note, I kindly request everyone to rise for Tamil Thai Valthu, a lyrical tribute to our motherland.
Thank you. you everyone. Please be seated. Today, we are pleased to host an expert panel from Celeros Flow Technology, sharing their expertise in pump technologies. The session will focus on specialized pump topics from both original equipment and aftermarket perspectives, offering valuable insights for professionals involved in pump design, operation, and maintenance. We begin the technical program with 2 sessions on pump performance and lifecycle optimization. The first presentation, Pumps Original Equipment, that is high energy pumps and CO2 injection pumps, will be jointly delivered by Mr. Scott McAllister, Pump Product Manager, and Mr. Gauri Shankar, Regional Sales Manager, Pumps OE. This session will cover high energy and CO2 injection pump applications, key design considerations, and operational challenges. The second presentation, Pumps Aftermarket, that is pump upgrades, re-reads, and field experience, will be presented by Mr. Callum Scott, Techno-Commercial Lead at Celeros, along with Mr. Sanjit Das, Regional Sales Manager, Pumps AM. It will focus on aftermarket solutions to improve performance, efficiency, and equipment life, supported by field experience and case studies. On behalf of Tamil Nadu Engineers Forum 2026, I warmly welcome the distinguished speakers and the participants. We look forward to an engaging and informative technical session. It is with great pride that we announce TEF's 27th year of excellence. This milestone will be commemorated through our flagship events, the 10th Engineering Excellence Awards and the 17th Technological Innovation Conference and Exposition, scheduled on 1st October 2026. We look forward for your valued presence and continued support in making this a memorable and a successful occasion. On behalf of TEF 2026 committee, we take this opportunity to convey our sincere gratitude to our sponsors. Your trust and continued support remain integral to TEF's growth and success. Our sincere thanks to today's event partners, Celeros Flow Technology. We gratefully acknowledge our presenting sponsors, KMMC, Golden Palm, Nori. Our heartfelt thanks to our platinum sponsors, Aldora, Al-Arfaj Engineering, KUF, Satco, and TransW. We also thank our gold sponsors, Al-Bella General Trading, Al-Mula Exchange, Burgan Bank, Eagle Berman, Gulfspic, Hisco, Mahata Trading and Petroleum Services Company. Finally, we thank our silver sponsors, AGTC, GTC, Rank, Albarion, Saravana Bhavan, Old Tech, Malabar Gold and Diamonds. We also wish to thank our health partners, Shifa Al Jazeera Fahil, for their valuable support. I also take pride in sharing that TEF is the only ISO 9001-2015 certified non-profit engineering organization in our region, formally registered with the Embassy of India in Kuwait. Over the years, TEF has consistently conducted its programs with the highest standard of professionalism, always prioritizing safety and the well-being of the members and the partners in every initiative we undertake. As a part of our safety movement, I would like to highlight the safety exits in the conference area. Please note there are 4 emergency exits in the conference. The first exit is the main entrance through which we enter, and the second one is located to my left next to the display. And in addition, there are 2 exits located at the back of the stage, one to my left and one to my right. Kindly note these exits in case of emergency. With a continued commitment to safety, it is my responsibility to share the safety moment of the day.
We live in a world beating with urgency, breathing with difficulty, breaking under necessity. We are a society consumed by technology, compact in proximity, choked by inactivity. We are global. We are responsible. We are trending. We are too inactive. Everyone, everywhere, every day. We have a plan. It's time to activate our governments, to activate our environments, to activate our society, to activate ourselves. It's time to activate movement.
Proud members of the TEF community, we remain committed to creating meaningful value in all that we do. Through each program, we aim to enrich our members by drawing inspiration from the river Tirukkural, a timeless treasure that continues to guide and inspire Tamilians around the world. The Kural of the day is from Adhigaram Avai Anjamai. Kural 722. கற்றார் முன் கற்ற சில சொல்லி தாம் கற்ற மிக்கார் முன் மிக்க கொளல். குறள் விளக்கம். அறிவுடையவர்கள் நிறைந்த அவையில் நாம் கற்ற விஷயங்களை அவர்கள் எளிதில் உள்வாங்கிக் கொள்ளும் வகையில் மிக தெளிவாகவும் நேர்த்தியாகவும் முன்வைக்க வேண்டும். அதே வேளையில் நம்மை விட அனுபவத்திலும் அறிவிலும் சிறந்த வல்லுநர்கள் இருக்கும் இடத்தில் மிகுந்த ஆர்வத்துடன் அவர்கள் தரும் மேலான கருத்துக்களை கேட்டு நம்மை நாமே மேம்படுத்திக் கொள்ள வேண்டும். Translation. The Kural outlines a dual speed strategy for growth. To an audience of peers, you must be persuasive communicator, ensuring your ideas are sold or delivered successfully. However, when we encounter those with superior expertise, you should switch to being an active listener, treating the encounter as an opportunity to upgrade your current knowledge base. In simple words, be a teacher among peers, be a student among masters. And with that, we now move into the technical seminar, the very heart of today's gathering, where learning, knowledge sharing, and meaningful discussions take center stage. To begin this core segment of our event, our first session is on the topic pumps, original equipment, high energy pumps and CO2 injection pumps, presented by Mr. Scott McAllister, Pump Product Manager, and Mr. Gauri Sankar, Regional Sales Manager, Pumps OE from Celeros Flow Technology. Before inviting our speakers to the stage, it is a distinct honor to welcome Ms. Vijay Menon, Sales Director for the Middle East, Caspian, North America and Turkey at Celeros Flow Technology, to Tamil Nadu Engineers Forum Kuwait 2026. A seasoned leaders with nearly 3 decades of experience in oil and gas, petrochemical and power sectors. Ms. Vijay has built an impressive career, driving strategic growth and technical excellence across global organizations such as SPX Flow and John Crane. Her deep expertise in account management and engineering sales has made her a key contributor in navigating the complex energy landscapes of the region. It is my pleasure to introduce Mr. Scott McAllister, Pump Product Manager from Celeros Flow Technology. Mr. Scott is an accomplished engineering leader with over 15 years of deep technical expertise in mechanical design and flow technologies. Currently serving as the Pump Product Manager at Celeros Flow Technology in Glasgow. He has spent nearly 2 decades solving complex engineering challenges for global leaders such as SPX Flow and Clyde Union Pumps. He holds a bachelor's in product design engineering from the University of Glasgow and an MSc in Mechanical Engineering Design with distinction from Glasgow Caledonian University. Please join me in welcoming a true specialist in engineered solution and product management, Mr. Scott McAllister. Also, it is an honor to introduce Mr. Gauri Sankar S., a distinguished leader in the global flow technology with nearly 2 decades of specialized experience. Mr. Sankar currently serves as the Regional Sales Manager for New Business at Celeros Flow Technology in Dubai. where he is driving force in providing reliable pumping solution for the oil and gas industry. His career is built on a deep technical mastery of pumping systems, spanning almost 2 decades of industry leadership. Before transitioning into his current regional leadership role, he spent almost 10 years with Flowserve Corporation, where he progressed from application engineer to senior application team leader for power and desalination. His expertise is both brand and academically recognized. He was named the topper in the Asia Pacific Pumping System Analysis Program with an outstanding 94% score and holds advanced certification in pump and seal fundamentals. Today, he joined us along with Mr. Scott to share his high-level perspective on the evolving demanding of energy sector. Please join me in welcoming them to the stage.
Hello everyone. So first of all, எல்லாத்துக்கும் வணக்கம். So myself Gauri Shankar as a member has explained. First of all, before we start, I would take 2 minutes to thank TEF for accepting us. Special thanks to Mr. Rajendra Kannan and also Mr. Saravanan for giving this opportunity to host us in front of the esteemed team members of TEF. So here just 2 minutes before we start with the presentation. So we are making a lot of pumps from our company, but நாங்கள் உங்களுக்கு 2 pump pick பண்ணிருக்கோம் because to give the new technology to the emerging market. So that is our focus. So நாங்கள் 2 pump choose பண்ணிருக்கோம். First pump பார்த்தீங்கன்னா high energy pumps. What we can give different solutions to the on the current pumps comparing with the other manufacturers, so that it gives benefit for you guys during the maintenance and the operations. And the most important pump we are talking about CO2 pumps. And the pump ஏன் நாங்கள் கொடுக்குறோம், அந்த presentation ஏன் கொடுக்குறோம் அப்படின்னா, like what we are giving for the future generations, because we are polluting the world. So of course everybody has a concept to move to net zero. Net zero அப்படின்னு பார்த்தீங்கன்னா it's like balancing whatever carbon dioxide we are emitting from the day-to-day operations, we are equally generating the oxygen. So when both are getting neutralized, that is called net zero. So இப்போ வந்து நிறைய CO2s produce பண்ணிட்டு இருக்கோம். So how to optimize that and how to use the CO2 which are produced from the normal operations, அதை utilize பண்ணி how we can day-to-day improvise the existing production of oil and gas. So அந்த concept தான் like CO2 injection pumps யூஸ் பண்ணுறோம். So what is the criticality of the pumps? அதை கொஞ்சம் நாங்கள் பேச போகிறோம். And also what are the special features we have done for our design. So அதுவும் வந்து presentationsல cover பண்ணுறோம். So for our interest of our colleagues, so we will be doing the presentation in English. So with that, I will ask Vijay to start with the presentation about the company, followed by the pump OE presentations by myself and Scott. Thank you.
Thank you, Gauri. Good evening, everybody. Thank you for taking time to come here and join us for this meeting today. And I thank again the organizers of TEF. As you've already got my introduction, so my name is Vijay Menon. I'm the sales director. So today we'll start off with the agenda. As Gauri just mentioned, we have a very short time today, just about 2 hours, so we'll try and fit as much as possible. So we've got we'll try and maintain the time as much as possible, okay? So the first we'll start with the safety moment, and going on to the introduction, which I will cover in very few slides. Then we will go into the original equipment, basically the BB5s and CO2 injection. These are typical applications, critical applications. We are very good in engineering when it comes to these products. These are our niche products. Pump upgrades and re-rates we have, and you will see the experience that we have had over the past 50 plus years in this country. We've got a number of installations in oil and gas as well as the power and water sector. So what is it, how can we actually bring in reliability and efficiency for the equipments that have been installed and operating at site for over 50 years? And then we will just give you a brief introduction to our service center, which is based out of Abu Dhabi. So, coming to a safety moment. Now, at Celeros Flow Technology, it is given the highest priority. And we always talk about safety whenever we start, and I hear TEF have got the same values as well. So coming to today's session, we are going to talk about exits. How important is exits, right? So when it comes to, sometimes it's just about knowing your exit and all it takes, right? So we all know the exits at home. We know the exits maybe at a shop. But how many of you know the exits of a mall, perhaps? And any major events that you take your family to, right? So today, what we want to share is that, please make an effort to understand your exits. If you do understand your exits, probably you have a better chance to get there first, right? And imagine the number of people in a mall or any other big places where the number of people would have to get to that exit. So if you know the exit, you probably will be in a better chance to get out first. So that's for today, is safety moment. Okay, all right, so who is Celeros Technology, right? So Celeros Technology has got about 150 plus years of experience, right? We go back 150 years of experience, I would say. So it's an engineered product manufacturing company. It's a mission critical control solution providers, right? That's what we are. And we value ourselves as life cycle partners, right? When we call life cycle partners, we actually work with our end users, with our customers, right from the design stage, whatever the challenges are, right? When it comes to upstream challenges, downstream challenges, midstream, nuclear, defense, power and water. Now, right from the design stage, we work with them in order to design the equipment, work with the spec, manufacture, supply, and then do the aftermarket support services for the equipments that we supply throughout the life cycle of the plant and the equipment. So that's what we do, and then that will give our customers, our end users, a reliable and a sustainable supply chain. So when it comes to products, we have these are the products that or rather the brands that we have. Today we are going to talk about pumps. Now, under Celeros Flow Technology, we have pumps, we have valves, and we have GD. When it comes to pumps, we make the full range of API 610 that comes under the Clyde Union pump family. We also make API 674 and 676. Now, API 610 is a complete centrifugal range. 674, the reciprocating pump range, and 676, which is basically the positive displacement, the screw type pumps. They come under the plenty ranges, and the SNN pump are basically the submersible pumps for the offshore marine industry. We will get that, we'll give you a little more details into those pump types in a while. My colleagues will explain those categories to you. The other ones, the other product lines that we have are Corpus Vulcan. These are basically check valves. We have these superheaters in Corpus Vulcan. And in M&J, we have surge relief valve, diverter valves, gate valves, check valves, control valves. And then when it comes to GD engineering, they are pig launches and signalers, and we also have closures, band lock closures and the quick closures for pipe maintenance. So in terms of the sectors, as I said, we serve upstream, downstream, midstream in terms of oil and gas. So energy transition is another area that we serve. Power, defense, we cater to the oil and gas, water, and the chemical processing. So I want to just dive into a little bit more about the Clyde Union pumps itself. Now you must be thinking, what am I talking about 150 years of experience? Now you may have not heard about Celeros, or maybe some of you have, but not maybe all. So I just want to give you a brief understanding about our legacy, and you may have come across some of these pump brands. So it all started back in 1871 when the Ware Pump was actually founded. So the Ware Pump was such a big company that they wanted to sell the upstream side of the pump company. At that time, back in 2007, there was Jim McCall, his name is, he was basically an entrepreneur. He wanted to invest into the oil and gas. So at that time, Ware decided to sell the upstream side of their business. So he bought the upstream side of the pump company, and he named the Ware Pump as Clyde Pump. So that's how Clyde Pump, the name, came into existence. But if you see over the bottom line here, they're all the Ware company acquired these brands over a period of time, right? So under Ware brand, there was Harland, Mather & Platt, the Ware W.H. Allen. All these were the different brands that came along when he bought the upstream side of the Ware business. So we hold the IP for all the brands that the Ware had acquired and that they had manufactured in their Scotland facility. So Jim McCall, who named the Ware pumps as Clyde pumps, he bought the Scotland facility, and when he bought the Scotland facility, he acquired all these brands and all the IP that came along with it. So even today, there are some of these brands which are actually operating in some of the fields, and we continue to support those equipments by providing the aftermarket services. And along the same timeline, you see on the top, there were Union Pumps. He was an entrepreneur. He got the upstream side of the pump business, right? So he wanted to expand the business, and he wanted to get into the downstream side of the pump business as well. So at the same time, the Union Pumps were up for sale. Now, Union Pump at the same timeline had acquired a lot of other brands as well. So they had David Brown, Ginnard, Union Pumps, Textron. So all these were the different brands that they had bought, and it was a Union Pump family. So when he bought Union Pump and he merged the Union Pump with the Clyde Pump, which was basically the Ware Pump, he joined those two brands together and he called it as Clyde Union Pumps. So the Clyde Union Pumps as a name came into existence in 2007, 2008, but then you can see the heritage of 150 years of experience that came along with it. So although the name of Clyde Union was only formed in 2007, 2008, there's 150 years of experience that comes along with it. Then in 2010, 2008, we have a joint venture that was formed in India, and then we acquired SNN Pumps in 2010, and in 2012, Clyde Union was actually sold to SPX Flow, right? So the SPX Flow acquired Clyde Union Pumps, and but however, the brand name existed. We were registered as Clyde Union Pumps with all the end users, and even today, that brand as Clyde Union exists, and our name, if you look at the ABL, it exists as Clyde Union Pumps. Then in 2020, we were acquired by Apollo Global Management. It's an equity company. Was the power and energy division of SPX Flow was divested, and Apollo Global Management bought that part of the company. And that's when we were called as Celeros Flow Technology. So the Clyde Union Pump became one of the brand under Celeros Flow Technology. So when it comes to factories, as I said, we have 1886, that's when the Glasgow factory was built. And even today, the pumps are manufactured in the same factory, and it is based out of Scotland. And this is where we manufacture all the high energy pumps for the oil and gas industry. Then we have David Brown and Guinard Pumps, which was built in 1970. That's in Annecy, France. That's on the top. And even today, all the Guinard pump heritage, or rather the hydraulics, we continue to use them. And that factory supports the nuclear applications and the oil and gas applications for the France domestic market. In 97, the Union Pumps the factory was built, is also where we manufacture pumps. It's in Canada, Burlington, Canada. So here we also have nuclear certification. We manufacture pumps for nuclear industry as well as the oil and gas industry. And then we have the factory in India, which is in Ghaziabad, where we manufacture the low energy pumps. And that's where you see here. That's in Ghaziabad. So again, these are the pictures of the original when the pumps were invented, I would say. So it all started with the shipbuilding company, and then and that evolved into the pump and then the wear product as such, right? So that's what it says about 150 years of history, and it all started with the shipbuilding. And these are the brands these are the heritage brands, and we continue to supply and support these hydraulics and also these pumps that are installed in various plants. We continue to give the aftermarket support and services to them. So that's it from me today. It's just a brief introduction, and I let my colleagues take you through the original equipment and the aftermarket services. Thank you very much.
Thanks, Vijay. So, like the next few slides will cover the product range, what we make from Clyde Union pumps, the current manufacturing ranges and the facilities. So to start with, we on the high energy side, which is on the upstream side, we make the water injection pumps and the main oil transfer pumps, which are on the upstream oil and gas business, which is supported by the booster pumps, the BB1 type pumps, and the BB3 pumps for the oil transfer pumps, and supported also by the VS6 pumps and the VS1, which is for the seawater intake and for the booster applications. So these are the critical products we make for the upstream business in the oil and gas, and out of which the BB5 is our flagship product. Whatever engineering, it's a completely customized pump. So whatever you need, we can make on those pumps, and I think Callum will be covering on the high energy pumps, where with our extensive experience, what differentiate we can make for you, and what betterment solutions we can give for you in the high energy pumps. And on the mid-range, midstream and on the downstream applications, we give also ABS 610 pumps, which are widely used for the process applications. So starting with the OH2s, BB2 pumps, and the BB3 pumps, and the VS4 and the VS6 pumps. These pumps are manufactured from our India facility. For the low energy pumps, like we can say up to 100 bar, we term it as low energy. So these pumps are manufactured from our India facility. And anything beyond 100 bar, it is developed and manufactured by our flagship facility, which is in UK, operating for 150 years. So in terms of the facilities what we have, as Vijay said, like currently after we acquired a lot of companies over a period of time, and after a lot of optimizations, we currently have 4 manufacturing facilities actively producing API pumps and the nuclear pumps. So the UK facility in Glasgow, followed by France facility, and the Canada facility are nuclear certified facilities as well. So which means that they are N certified facilities. They have gone through a stringent qualification process to deliver the equipments for the defense and the nuclear business. And our India facility is a ISO certified facility, mainly delivering and focusing on the oil and gas business, downstream part of it. So in terms of to give a very glimpse idea about how big is the facility is, our UK facility can test up to 9.5 megawatt pumps in terms of testing capacity, and they can hydro test up to 950 bar pressure, and they can performance test the pumps up to 500 bar. So coming to the next facility, which is France and Canada, both are like similar range of testing facilities they have, which is up to 4.5 megawatt. And they cater the business for midstream and also for the nuclear and defense projects. And the last facility on the list, which is operation since 2008, is the India facility, which can test up to 1.6 megawatt of power requirements and up to 100 bar in terms of pressure rating. So in terms of approved vendor list, as Vijay said, like even though we have been acquired by SPX followed by Celeros, our registered facility names has not been changed since 2008. The registered facility names are Clyde Union Limited in UK and Clyde Pumps India, and Clyde Union Canada and Clyde Union France. So currently with K tendering, which is obviously KOC and KMPC, we have been registered with all the 4 facilities has been registered with KMPC and KOC, and of course in K tendering now. And of course with other Middle East major end users I have listed, so we have been registered with almost all end users in the Middle East sector. So with that, I will ask 1 minute Kanar to introduce about their facility, who is our local partner in Kuwait, followed by the high energy presentation from Callum, and also about the CO2 pumps, injection pumps.
Thank you, Gauri. My name is Khalid Parker. I've been working as a team leader for Kanar and supporting the Clyde Union business, namely for the new equipments as well as the aftermarket, and expanding the business in Kuwait. If I talk about Kanar, we have been established in 1970, namely to serve the hydrocarbon sector in Kuwait. Our partnership with Clyde Union Pump is over five decades, I would say, more than 50 years. And I would be proud enough to say that we have delivered pumps from Clyde Union Pumps in Kuwait, which have been running for over 50 years. This shows basically that how reliable the pumps are being delivered by Clyde Union Pumps. If I talk about Kanar, which is around 50,000 square meters, and we have been also approved as a first-class local EPC contractor. Thank you.
Okay, hi everybody. Thank you very much for having me again. As the guy said, my name is Scott McAllister. I'm based in our facility in Glasgow, Scotland. I appreciate I have an accent. Callum Scott, you'll see he also has one, so I will try my best to keep things nice and slow and not get too fast in terms of presenting. But again, thank you very much for having me. I'm a member of the mechanical engineers in the United Kingdom. We also do similar events like this in Forum, but on a much smaller size. You guys are doing a fantastic effort with the amount of people that you obviously have within your forum, so congratulations on that. So, what we want to cover today is very much focused on high energy pumps, and very much that circles around the BB5 multi-stage barrel type pumps, is what you can see here in the sectional arrangement drawing a cutaway that we have here. So BB, for those that don't know, stands for between bearings. Multi-stage, in terms of the number of impellers within the pump on the shaft. We would then have matching diffusers and ring sections within the pump itself, and then all encased within effectively what we term a barrel casing within the pump. Traditional other features within it, mechanical seals at both the non-drive end and the drive end. You would have journal bearings supporting the shaft at each end, and then a tilting pad thrust bearing located at the back end, taking any of the residual hydraulic thrust that we tend to have within the pump. So again, this is very much used in typical applications like seawater injection, produced water injection, main oil line, and also condensate export. And some of the new markets that we've started to see is CO2 injection from an energy transition perspective. The key benefits of this type of pump is that effectively it's a cartridge withdrawal design. So in essence, the suction and discharge pipework here and here can basically remain in place, which means that under maintenance, effectively the full cartridge can be removed from the barrel casing itself. The suction and discharge pipework do not need to be disrupted, and effectively a spare cartridge can then be effectively inserted into the same barrel, and continuation on with effectively production or seawater injection. One of the main areas that we kind of tend to focus on within our pump design is what we refer to as the shear ring design. So this is the shear ring in the sort of light blue colour here within the barrel and the end cover. And effectively what this allows is, rather than having a very, very large number of kind of heavy duty bolting around the end of the barrel itself, it allows these four segmented rings to be effectively removed from the barrel, and that allows basically the whole cartridge to be removed from the barrel. This can be done in a very, very short period of time, roughly about one shift. So that allows effectively a cartridge to be removed, a new cartridge or a replacement cartridge to be inserted, and then production can be basically re-established. So again, a very, very key design feature for what we need. So what we tend to find is that maybe customers would have, say for example, 3 water injection pumps with 1 spare cartridge sitting always in stock on the side. And then that allows them, if they do ever have any issues from a maintenance perspective or planned maintenance, they can then remove the cartridge, replace the side cartridge, and then the other cartridge can be brought into a facility for refurbishment. Yeah.
Hello. So to add more points on this particular slide is like the BB5 pump, what we have shown here is a completely customized pump. So you name any requirements on this pump, we have a solution to offer. So as you see in the picture, the first on the left hand side is an inline BB5 pump, and the same pump can be offered in a back-to-back arrangement, which is on the right hand side. So these are diffuser pumps. Also we have a volume design as well. and the top configuration can be also customized based on the piping layout. If you want side, bottom top, or side top, whatever configuration you name it, we can offer it. And also latestly we have giving a solution for 8 times nozzle load as well for the pumps if there is a more piping load coming onto the pump itself. So it's a completely customized pump. So whatever issues you have, we can give it. And in terms of the shearing design, which Callum explained, the traditional pump, as you see on the right hand side, it's surrounded with the discharge cover, which is fully bolted, heavy bolts, super bolts, and it needs around roughly about 3 shifts to completely remove it and insert a new cartridge and put back the cover. But with the shearing, with 1 shift, it can be done. So basically, it is like downtime is very short with the shearing design. But only thing is like it has to be specified onto the tender because it's a little more expensive. But if you look at the OPEX, operating cost expense, that will be the best solution to which we can offer to the end users. And once the end user starts using it, they like it and they keep on repeating it. They want a shearing design, which has been widely used by a lot of end users like BP and ADNOC in offshore applications. Thanks, Karan.
Thanks. Okay, so what we have here is basically our engineering capability, but just from our Glasgow facility, which is where I would say is, as VJ covered, is very much focused on a lot of our high energy oil and gas type projects. We do obviously have engineering departments at our Annecy facility, our Burlington facility, in CPIL in India, and also we have a Bangalore engineering centre as well with a high level of engineers that basically supports all of our facilities. But as you can see here, we use kind of what we refer to as a kind of holistic design methodology, because as you guys will fully appreciate, and as Gary touched on there, a lot of the work that we're doing is custom engineering to order. It's working with customer specifications and taking that approach. So very much the inputs, it's never a kind of straight line effectively from input to output to qualification. There is a very much an iterative process involved of going back around that we'll kind of touch on going through this presentation. But very much our expertise is focused around our kind of heritage background on hydraulic design and analysis, noise and vibration, rotor dynamics, again a very specifically once we're getting into the high energy sphere of kind of pump design, these things start to become exceptionally important. Stress and structural analysis, a huge amount of that is done. Metallurgy, again we are seeing more and more playing into difficult markets, difficult pumped mediums, handling more and more solids and challenges there. And as things progress with things like foundries and coatings and advanced metallurgy, we are starting to see a lot more come from that. Electrical engineering is a huge part of also what we do. We have specialists in that. A huge proportion of the pump skids that we'll kind of show you are basically the electrical side of it, electrical motors, transformers, VSDs, that type of thing. And again, experimental and prototype testing that we'll share a little bit of. Yeah. So again, this slide here is very much focused on our expertise from a hydraulic design, very much the heart of the design. Again, we use a series of different approaches, both from our in-house developed software. So these are proprietary software that we've developed over many years that allows us to, search our hydraulic databases, make informed selections for pumps going forward, and effectively predict what is going to happen from a pump performance test perspective once we get the pump on our test bed and then ultimately out into the field. We also use third-party equipment, things like turbo design, and things like that for generating new impeller and volute diffuser designs. And then also as industry has moved forward, we use a full suite of computational fluid dynamics, CFD type of, mostly ANSYS CFX for that. Thank you. Yeah, So keeping on the theme of analysis, stress analysis, a huge amount playing within the energy transition and the high energy pump sphere. We see a huge amount of requirement on effectively analysis from stress perspective in terms of both material stress and deformation. So we look at things like pressures, pipe loads, seismic, thermal and fatigue, all attributed into our models from a 3D perspective, and then analysis of the results going forward. So again, a huge amount of work is done up front within our engineering teams and massively supported by our Bangalore Engineering Centre. Rotor dynamics, again, a huge part of this being high speed, specifically when we're looking at drivetrains as well, inclusive of motors, gearboxes, and obviously the pump itself. So again, a huge amount of work is done on that from a lateral and torsional rotor dynamic perspective. Again, the key to this is doing this up front rather than trying to go down the route of not doing it and then finding out you have issues on the test bed, test facilities, and then have to work your way back. I think the key to what Gauri said is the custom engineered nature of the pumps. Every single pump that we do is subtly different to each other. We are not a mass manufacturer of pumps, so therefore every single one of them has to be going through effectively a thorough check from a rotor dynamic perspective. Structural analysis, again, modal and harmonic structural analysis are completed, again with key to avoiding effectively vibration and any resonance that we start to see within the structures and surrounding areas. Acoustic analysis, again, a huge amount of that is done modal and harmonic to look at pumps, the impellers, and again, a huge part of that is the associated pipe work. We're looking at that. So again, looking at taking things like crossovers on BB3 casings, impeller, wet end modals, analysis, and again a huge amount of work done on that and using our expertise. And this very much focuses on that iterative approach that I explained earlier. So looking at things like the design inputs, so the target performance that the customers would have in terms of flow head data sheet requirements, any space envelope that we would be given. And then we would work through our kind of traditional, mode of operation. So using things like some of the pump design codes that I referred to, design layouts in terms of SolidWorks models, and the Turbo Design Suite that we have in-house, then ANSYS CFD models, parametric modelling, and then ultimately a predicted performance, what we expect the pump to do once we have effectively assembled and designed it. And then obviously the design outputs out from that, the things like the 2D drawings, the 3D models, and the performance test curves that we would be looking to achieve. And again, the very key to that is that we spend a whole load of times going back around this loop, trying to ultimately optimize the solution for what we have.
I'm adding to the point, during the 3D model reviews, we participate with customers on 3D models at different stages of time, 30%, 60%, 90%. And also during the P&ID review, and also during the HAZAP review. So it's just not, because these are high energy pumps, so there will be a lot of inputs required and will be given from us to the EPCs during the HAZAP as well as during the 3D model reviews as well. So that's always a part of the critical equipments, and especially for this high energy BB5 pumps.
So again, this is just an example when we talk, high energy. This is effectively what we mean by high energy. There's types of pumps here. You can start to see flows and heads of what we would typically see high speed application. This one with again optimized, looking at things like the suction guides, suction passageways, the diffuser design, and obviously the kind of upfront impeller design, all designed to achieve as an efficient as approach as we possibly can to a pump design. And again, we're talking, in the ballpark of anywhere between sort of 15 megawatts on this application here. So this is really what we mean by the high energy sphere of the kind of pump application. So So again, one of the things I talked about up front was the kind of R&D side of what we do. You can see here is the pump in the background here. That was the pump. You can see here is the pump in the background here. That was the pump that you saw before. And what you can see on the bench here is what we refer to as our kind of fast test rig. And that's a kind of allows us to test hydraulics using basically 3D printed components in a test loop in Glasgow to know that under scaled conditions we can meet the hydraulic performance requirements of where we are, and we can do so under a hugely reduced time frame rather than waiting for foundries and that type of thing. This is our research and development laboratory based in Glasgow. So again, this is a bit of an engineer's kind of playground with loads of different just little bits of pipes and tanks, etc., where we modify and build individual test rigs and things like that, which again allows us to basically engineer and design different components and designs that we want to do. And again, we have a full staff of research and development engineers that work within Glasgow, and again are working hand in hand with the engineering facility there. So this is our general, Gowrie touched on it in terms of some of the things from our test facility capabilities here in Glasgow. So again, some of the numbers that we touched on, things like hydro testing up to 950 bar. We're talking about powers and well up into the towards the 10, 11 megawatt areas. And again, that's testing full speed, full power, which again, not many companies can do. A lot of companies will test at reduced speeds or reduced powers and then effectively scale the test results. This allows us to do specifically, just really test pumps so that when it does go to site, we can have a very, very high degree of confidence that the pump is going to meet both the mechanical and hydraulic performance requirements before it actually even goes there. So some of the, again, I don't want to touch on every single one of these, but really what the kind of key takeaway message from here is that these are some of the major milestones that we've achieved from as effectively as a pump company within the oil and gas market. So really the kind of probably the key ones here is since 1975, because of our location in Glasgow, Scotland, we've had a very, very key kind of tie-in to the North Sea offshore oil and gas market. So we had the first pumps that basically brought the UK North Sea oil back onto shore from the BP Forties field. And over the years we have very much worked with individual customers to achieve firsts in both things like water injection, seawater lift, firewater pumps duties, main oil line pumps, pumps below the seabed from a hydraulic submersible pump perspective. And also latterly we've become much more involved in the kind of high energy side of the market. So things like the Norsok barrel requirements, casting the largest BB5 barrel casing in super duplex stainless steel, the ultra high pressure barrel, that we'll talk about that from a new product development point of view. And then latterly the world's highest pressure and largest CO2 pump at 550, that should say bar, apologies. So this just gives you an idea of where when we say ultra high pressure, this is what we mean. So we very much worked in partnership with SPM to develop a ultra high pressure injection pump. So this one here is basically flow and head on X and Y axis, and you can see our kind of historical legacy database of where our pumps have normally operated. The ultra high pressure was well in excess, as you can see, of their basically effectively 30% higher than any of the pumps within our installed base. So again, we had to use that iterative design process to come up with a pump that was as effectively as efficient as possible, utilising a back-to-back design that we have there in terms of a configuration. So again, high speed operating, roughly about 6,000 RPM, and again, a huge amount of significant challenges had to be overcome on that project. Things like sealing, hydro testing, even manufacturing components of that level of thickness at the kind of material requirements that we would require. Again, just a picture of the actual pump itself on our test bed in Glasgow. So again, we took this wasn't just a conceptual 3D model design. This was actually something that we did as a prototype. Manufactured every single component, tested at full speed, full pressure, and the results were excellent. So that is a project or a product that is now within our armoury and is feeding into a lot of other projects that we see within the market as the oil and gas has been moved much more into the higher pressure injection market. So what I want to touch on now is some of the word that we refer to as packaging. So when I mean packaging of the pumps itself in terms of as pump skids. So here are some of the examples that we've done for ADNOC Middle East. We have, and again, probably the key takeaway here is that 3 different projects, and as you can see, all 3 are completely different. No 2 pumps are exactly the same, and that I would make that statement for the actual pump design itself, but also for the actual package itself. So this is where we would take up to 200 specifications. We would then apply those to the project and basically build a customized engineer-to-order solution for companies such as ADNOC. Again, you can start to see some of the examples for Missan Oil Company and Saudi Aramco here. Again, we have in Europe. Again, it's not just focusing on the Middle East. This one here is for this was Mariner in Norway. So again, a very, very complex package where we had to fit within a quite a neat footprint. Let's just put it that way. We also had to have very, very strict requirements from a noise perspective. So again, a custom engineered solution for an acoustic enclosure. So again, a huge amount of work done, put up front to effectively get to the stage of a 3D model, and then ultimately having the pumps packaged in a custom engineered option for the customer in line with their requirements. Again, another one from Africa in Gina. So again to touch on things like the a very, very complex network of pipework from lube oil systems, coolers, seal systems, gearbox, electric motor. Again, this one here was a 10.6 megawatt ABB electric motor, giving you kind of an idea of power. And again, a very, very large package, total package weight, just shy of 90 tons. So again, a significant challenge. And this is an image of us taking the full pump set itself, taking basically from 3D model to the pump set itself in our test bay, and basically testing at full speed, full pressure, with basically everything included. So things like the pump, gearbox, motor, VFD, transformers, lube oil systems, acoustic enclosures, everything effectively done so that the customer has confidence that when it's installed back at site, everything has been fully tested and everything is all good and basically meets their requirements. Again, this one here was again another example of where we've taken a water injection pump. This one here a little bit more simple, direct drive with an electric motor, a lube oil system. But again, the challenges of having that is taking that into our test shop in Glasgow and doing a full string test. Again, this one here we have basically just a kind of summary of, if I just move these on, again it gives you, this was an example where we had the lube oil system and the air blast coolers located off skid, but the customer wanted to utilise this as an option of testing within our facility, using basically it as a full string. So we moved effectively the pump skid itself into the test shop, did the test on that, and then that was all hooked up with the lube oil system and air blast coolers all within our test shop. That was then. So on the energy transition side of things, this slide here really just gives from a capture, transfer and injection perspective all the different pump types that we have within our range and where it fits within the energy transition from a carbon capture and storage perspective.
Callum, just to add on the capture and for the, can you go to the previous slide please? So on the capture and transfer, those are like very standard, pretty standard pumps, which is from the API market, and with a pretty standard seal system, because the capture technology will be using the amine solution concept for capturing the CO2s. But the specialty where we can give an engineered solution is on the injection pumps, which is completely different from standard API pumps, because whatever you have seen in the previous slides, those are water injection pumps or main oil transfer pumps. So if there is any leakage, at the max it could be like a little bit hazardous to it, but if there is a leakage in the CO2, which we'll be covering in the next slides, the entire concept of the pump itself, the design itself is a failure, which means the entire project is failed. And on top of it, it is more hazardous because CO2 exposure, if there is any breakage of the seals and if it is getting exposed, it is hazardous to the people as well. So the criticality of the design of the CO2 pumps with the associated auxiliaries is very, very important. And on the recent ADNOC jobs which was awarded to us in 2024, we have done an extensive research together with ADNOC and with the Kent team who was the EPCM for ADNOC in developing the concept for the pumps and for the the seats itself. So, Callum.
Yeah, so this is one of the projects we've worked on in terms of energy transition. This was for REG or REG in the US. And again, it was very much termed as a kind of new product development for us, both in terms of our own skills and services for that specific market. The key here was that the company knew that basically the biofuel itself was going to be quite a challenging product to pump itself. They knew there was going to be issues with dry running of the equipment, so we employed a series of non-metallic wear rings into this application. And again, these are now installed at site, are operating exceptionally well for REG, which is now Chevron. And again, it opens up a huge market for us using our kind of traditional BB5 technology, but into effectively a biofuels market and that going forward. This one here, another one for Norway. This was for the Draugen field, where effectively these were, Draugen is not a new field. It's been probably installation from probably the mid 80s, 90s, maybe even before. But in essence, the main injection pumps were gas turbine driven. So basically the end user, OKEA, wanted to change over from gas turbine driven to basically electrification. So they basically organised running of an underwater cable to basically power the full oil and gas platform, and effectively wanted us to employ a cleaner, more energy efficient drop-in electric motor driven solution, which is what you see here. The key to this is that we had obviously because it's an existing platform, we had a very, very small space envelope for which to play within. So again, you can probably see, given probably some of the other examples that I've seen or I've shown you before, these were very much shoehorned into a very, very small space envelope. But again, the key to this is that over the approximately remaining 15 years of platform life, it's about 180,000 tonnes of CO2 reduction per year. So again, this basically became very much the follow-up for a future Nord project that we are working on going forward in basically the UK and Norwegian continental shelf. This one's actually quite an interesting one for carbon capture. We've been working closely with a company called Carbon Clean that are based in the UK, but are actually an Indian company in background. I say interesting because it's not actually a pump itself, it's a rotating packed bed. But in essence, just to kind of give a little bit of a summary, it's a bit like a technology of packing material here, which is rotated at a relatively slow speed to what we have. The proprietary software or proprietary technology from Carbon Clean is the solution that they basically put in from a liquid inlet perspective and is distributed out from the centre, and then basically returned back into a loop perspective. The gas inlet itself is done there, so it's across the packing in the reverse direction. So we have been involved because of our background in terms of energy transition and also rotating equipment to look at the design of both the absorber and the desorber for this project. So we are going through a very much a staged and gated development process, working hand in hand with Carbon Clean to produce varying different designs in terms of a number of tonnes per day. So touching on CO2 injection, this has become, as kind of Gauri touched on, quite an interesting area for our company going forward, because as I've touched on, we have a very, very proud heritage and engineering background on injection pumps, and therefore this has lent itself quite well to moving into things for CO2 injection. So CO2 injection is where we're normally injecting CO2 at a supercritical state, traditionally from a carbon capture or from an enhanced oil recovery perspective. We have developed a technology, if I can move this on, if that's all right. Yeah, so again, touching on to the supercritical fluid is where we've been tending to see. So again, the key to this is that it's under a very, very clear point from both temperature and pressure. And as what would normally happen with our pump, that can be adjusted very, very quickly. So from a pump perspective, there is a massive amount of challenges there in terms of the viscosity is actually varying as it goes through the pump from the suction into discharge. So what we've had to do is, if I just move this on, yeah, so really from a pump perspective, what are the specific challenges? Materials, we have a huge challenge from a materials perspective, both in terms of corrosion, but also in terms of rapid decompression from an O-rings or an elastomer perspective. As I touched on before, the CO2 properties, very, very small temperature changes can cause the CO2 to flash, and effectively then from a pump perspective, cavitation comes into play, and effectively we have huge problems with pumps. The density itself varies irregularly, which again is with temperature and pressure, which is not what we tend to see from a pump perspective. And supercritical CO2 is obviously often used at injection. So again, the risk of flashing and basically further issues surrounding sealings and elastomers. So again, a huge, quite a challenging application from a pump perspective. So we were awarded a project for a CO2 project within the UAE, where the customer had a very, very large number of different applications that they wanted us to look at and work on. This is basically what I touched on before about basically developing our first CO2 pump and the largest BB5 ever manufactured by Celeros. So very much leveraging our experience on a ultra high pressure technology, and then ultimately moving that over into a CO2 injection point of view. So again, we've worked very, very hard with the customer itself to work on effectively a stage-by-stage model. So basically every impeller within the multi-stage pump would see effectively a completely different fluid requirement from both a density, pressure and temperature. So again, we've had to build up ourselves an individual stage-by-stage model, and that would be ultimately iterated through. And then what we also need to do is try to work out, we obviously can't test on our test bed, supercritical CO2, so therefore we have to basically generate an estimate or a prediction of what the performance needs to be on water on test to basically allow us to proceed with basically confidence that what we are doing meets the requirements from both a mechanical and hydraulic perspective.
Scott, if I mind, let me add 3 points to here. So, as Scott said, CO2 is a compressible liquid and it is very sensitive to the temperature. So, in Middle East, we have winters going up to 0 degrees or below 0 degrees at certain areas, and summers soaring up to 50 or 50 plus. So, when you look at the one CO2 pumps which were under execution, considering the change in temperature, the pump are expected to operate at 24 different points because of the change in pressure and also the change in site conditions, the site temperature. And most importantly, once the CO2 is captured from the gaseous form, it is going to the compressors, it is getting compressed, it is sending to the supercritical formation, it will be reaching the pump for injecting. So we get the CO2 in the supercritical form, but for the mechanical seals, we take those CO2s in supercritical form, convert to gas, because the seals cannot be operating in a supercritical stage with the operating liquid. So we need to convert that into the gaseous, and we use the dry gas seal systems, which is almost the pump size. The skid size of the seal system is almost the skid size of the pump itself. So that's very, very tedious process, and in terms of designing. And the solution is now ready-made, available with us. And adding to the point, as Scott said, it's a compressible liquid. So once there is example, 100 meter cube of CO2 is entering into the inlet, you will not get the same amount of CO2 outside because it's getting compressed. So basically, you will be getting at 80 meter cube. So there will be 20% drop because of the change in pressure as well, and because of which the volumetric is also getting changed. So each stage of the pump is different from each other. So the pump sizing itself is a tedious process, and it needs experience, and only who has delivered the pumps will have those experience done. And as I told you, 2 years of R&D has been enormously put by our team to have a solution for this critical applications.
Thank you. Yeah, so this gives you just a bit of an overview of the design itself. As Gowrie said, we've removed the shaft here and the dry gas seals, but in essence gives you an idea of the kind of convoluted way. What we have here is actually what we would term a BB5V. It's effectively a volute design within the casing. Again, just gives that. We felt it gave that kind of more reliable hydraulic performance from a pump perspective, rather than, as I said previously, a diffuser style design. Okay, so again, key customer requirements, again, probably like all customers, safety, very, very much. CO2 leaks are obviously a thing that wants to be completely avoided. So again, that is very much at the top of the list. Reliability, low failure rates from a pump perspective are absolutely necessary to avoid customers accruing huge amounts of costs and for basically unplanned CO2 emissions. And ultimately efficiency from our point of view. Energy requirements for the system, there's no point in looking at it from an energy transition perspective and them not having effectively an efficient system. Okay, so that is us from an OE perspective. Want to do questions now, or?
It's question and answers for the OE. So.
Okay, yeah, thanks. If anybody has any questions or anything you want to go over.
So, good evening, Mr. Scott. So, this is Vivek Kumar, working in Gulfspeak as a lead rotating equipment engineer. First of all, thanks for your nice presentation.
Thank you.
So, my question is, since we are using high energy pumps, we are facing problems to meet this high NPHSR requirement from the vendor.
Yeah.
So, nowadays we are using a booster pump at the suction side.
Yeah.
So, do you have any technology to reduce this NPHSR?
Yeah.
So, what is the minimum NPHSR pump you have supplied for higher ratings?
Yeah, in terms of the minimums of what we would have, as I said, each individual design would have its own MPSHR curve. So it's very difficult to kind of provide a specific minimum that we've supplied a pump to. I can maybe provide you with maybe some examples of maybe some bookends of what we've done in the past, where different sizes of pumps, different speeds, different duties would have different requirements. So yeah, I could provide that after that, and we can have a look at it. Your point is well noted about the booster pumps, because we are seeing much more of that within the market to meet those basically requirements. Fully aware, we also supply pumps into the conventional power market, for example, where inducers are an established technology. So up front of the first stage in impeller, you would have an inducer. Fully aware that's not, from an API perspective, would be accepted. So fully appreciate we can't use that, but I think first and foremost, I don't think we're going to be able to get away from using booster pumps from that application. We are still going to have to do that. The key to it is basically trying to produce pumps using our experience and technologies to make effectively the best suction performance we possibly can.
Okay.
Thank you.
Actually, to answer that point, in the recent couple of projects, we had some solutions given by our hydraulic team. So we went with the direct drive options, so instead of high-speed options. So that could potentially has brought down the NPHR of the pump. And because of the footprint of requirements, site restrictions, we avoided the booster pump as well. It makes the high energy pump a little bit bigger, but the gearbox is getting avoided. So of course, we could be able to manage to fit the pump size into the skids available at site, the skid space available at site. So that possible solution is the direct drive option as well, without a gearbox.
Good evening. This is Ganesh Kumar from MAB, Rotating Design. I have a question with you. Thanks for a nice presentation. My question is recent development for the impellers, flanges and all made by 3D printing. 3D printing has several methods like sintered powder product, laser and so on. Yeah. Is it the proven design in supply to the oil and gas industries, and how long it has been in service?
Yeah. So, 3D printing for us, we have been working quite closely on it. We've been looking at it, we've been monitoring what other people are doing. As I said below, we've been doing it from an R&D perspective, from a fast test rig side of things. In terms of actually supplying 3D printed components such as impellers, for example, into the actual field and operating, that's not quite where we are yet. We've not managed to get to that stage. Where we are using 3D printing is in things like 3D printing of pattern equipment within the casting process to very much reduce the time it takes from effectively an order being placed on a cast component to actually receiving that cast component. So again, we're looking at that, but again, that is changing and evolving very much as we speak. We fully appreciate our competitors. We fully appreciate companies are spending a lot of resources and man hours on developing 3D printing, specifically in the materials of construction and at the surface finishes that are required for components like impellers and diffusers and things like that within pump components. So certainly something that we're working hard on. We are looking at it quite clearly, and I think over the next few years that will be things that you start to see a lot more of.
Thanks for the answer. One more question. Is it possible to make the casings, the volume type or the diffuser, through the 3D printing process?
Yeah. I mean, ultimately anything will ultimately become possible. I think at the moment, what is the kind of tried and tested methodology of either from a casings, like barrel casings, using castings, or what we're actually starting to see is much more of a move towards the forged options for things like barrel casings, just because it gives a much more reliable, metallurgical approach of what we're trying to achieve. So I think that's probably the kind of where we'll start to go. But yes, I think given in future 3D printing of these components may be something that we start to see a lot more of.
Is it economical than the commercial method?
I think, if I've understood you correctly, it's the technical versus commercial. Yeah, I think at the moment there are other technical requirements that go along with that. If you take impellers, for example, yes, the speed is of producing, a 3D printed impeller is significantly quicker than casting and machining it. However, when you actually factor in the full requirements of, for example, getting to the same stage of the surface finish of an impeller, we had to apply a huge amount of operating hours to basically get the surface finish that we required. So it wasn't like you just 3D print the component, take it off the printer and it was finished. A huge amount of work had to be done on dressing, etc., to get to the stage of that. So the cost from a kind of full life cycle perspective had to be taken into account from that, and actually cost-wise it wasn't actually that much cheaper doing it that way. So again, the key to it was very much the speed element of it. But again, I think that will be something as the technology evolves, surface finishes can start to improve, we might be able to see a bit more of a benefit come from there.
Thanks for the answer. One more question, sorry. Actually, we have injection pumps. Injection pumps are all reciprocating. If you want to use the centrifugal pump with the controlled injection rate, is it possible to make it without the spillback?
What was it? Without the
injection? You want to control or regulate the injection rating?
Yeah.
Without spillback. Is it possible to do it in centrifugal pumps?
Without a spillback? Without a spillback.
You mean you want to control the pressure or the flow?
No, flow. Actually, reciprocating pumps are having 0 to 100% throttling. So whichever required, we can able to control it through the knob or the lever.
Right.
Whereas in the centrifugal pumps, is it possible to, we want to, considering the frequent failures and frequent maintenance issues in the existing recip pumps, we want to go for the centrifugal pumps. In that case, is it possible to regulate through some means in the centrifugal pumps? That I want to.
Yeah, I think.
Recirculation. Yeah, so we have a recirculation recommendation. So you can operate the pump up to the minimum continuous flow, and the excess flow, whatever you have, you can recirculate it back. If you want to have the discharge fully closed, so that at least the pump should operate on the minimum continuous flow, at least that flow has to be recirculated back to the pump. We can't operate.
It's called spillback. Without spillback, is it possible to do it in the system pump itself, like throttling, the open the inlet or the control the inlet, control the vanes?
No, sir. Like the vanes are fixed. We don't have a modifying vanes on the pumps, so those are like fixed vanes. Like operating a pump below the minimum continuous flow, it will have its the vibrations of the pump will be higher. So that is the reason like we are sticking the minimum continuous flow like roughly about 30-35 points of BEP flow. So you can't operate below that particular flow recommended by us.
Yeah.
Thanks for the answer.
I'm Suresh from Kipikla. For the nozzle load, what software you are using?
Traditionally, for analysis of the nozzle loading, is that what you mean? Is that what you mean?
Yeah.
ANSYS mechanical normally we'd be using, so we would take the 3D model of, for example, the barrel. We would apply the various internal pressures. The nozzle loads would be applied there, and any other things like seismic or that type of thing would be applied, and then we would run through the analysis that way. So yeah, ANSYS mechanical for our software.
Thank you.
Yeah. Hi. Yeah. One more question, Mr. Scott.
Sorry.
Can you explain this pressure profile of the double casing? Actually, all the pressure parts are inside the inner casing, right?
That's correct, yes.
Yeah,
yes.
so can you explain the pressure profile of the inner casing as well as outer casing?
In terms of, what we would refer to as the ring section is what I believe you're meaning is the internal casing.
Whether all the casings are designed for MAWP or?
Basically, the external side of the casing would be 100% for MAWP, hydro tested up to 1.5 times MAWP. The ring sections itself, because of the nature of the BB5 design, basically they wouldn't actually be fully pressure retaining because it would be almost a kind of stage by stage. Basically, discharge pressure would be on the outside of the ring section design, and effectively, so you would have the differential pressure across the ring section itself, whereas it would be the external pressure that would be on the barrel.
Okay. And how these two casings getting separated?
Is it maybe easier to show can I maybe move back to an image there? That's right. Can I remove back to maybe I think it's slide. Yeah. Maybe a picture speaks 1,000 words.
Yeah, that's what.
Yeah.
Because many of the cross section we may not be able to see in that.
Yeah. Thanks. Yeah. So what you can see here in yellow is what we refer to as the ring sections. So those would be effectively stacked on top of each other and bolted onto each other. The barrel itself is this kind of purple colour here itself. So the full cartridge would be able to basically abut against this suction face here, and that would all be completely removed. Does that make sense? So that they're completely separate components in terms of the external casing itself and what you refer to as the kind of internal casing. We would build it in the vertical and we would effectively stack each ring section on top of each other that would be bolted. You can just see some of the kind of fasteners here. Thanks.
Hi Scott, thanks for the wonderful presentation. This is Altaf, civil design engineer from KNPC.
Yeah.
So we design we do dynamic analysis for pump foundations.
Yeah.
So you specified in your presentation that you are doing dynamic analysis.
Yeah.
So as a civil design design engineer's perspective, we will consider operating a natural frequency of the machine and amplitude. We will ensure that resonance should not occur. Likewise, we have certain rules for our design.
Yeah.
So you mean to say you are taking care of the foundation and frequency in your pump design?
Those would be supplied to us by the customer in terms of a specification. We would then apply those to our basically our pump skid to effectively make sure it can apply and can operate acceptably. So for example, some of the work we do in the North Sea, for example, or Gulf of Mexico, is for FPSOs, where, as you can imagine, the dynamic nature of FPSOs is quite significant, and we would then look at things like anti-vibration mounts, these types of things, if they have to be applied.
Yes, in FPSOs they will use that neoprene pads for anti-vibration.
Yeah, that's right. So it would very much be driven by the customer. The customer would provide us, probably somebody like yourself would generate a specification for what the pump would be expected to see from a dynamic perspective, and then we would apply that to our analysis, basically.
Okay, thanks.
Thank you.
Good evening, Scott. This is Saravana from Process Engineering, Kipik Al-Zur Refinery. As a part of carbon capture and transportation, we are carrying out the pre-feasibility study. In that, one of the item comes is the CO2 transfer, whether it should be considered as a liquid state or gaseous state. So how you will consider the selection of this process? Is it economical to consider only liquid, or we can consider compressor also?
In terms of seawater transfer, that's in terms of Euro?
No, not seawater, carbon dioxide.
On carbon dioxide transfer. No, I think it has to be looked at in the, typically it would be neither, it's specifically in the supercritical state is where we've been looking at it, because that is ultimately what it gets injected in. That's the state that we've been in. So again, it's neither. It's not that it's neither, but it's specifically within that supercritical state.
So in case of supercritical stage, what is the requirement is severe dehydration requirement is required, number one. And the second thing, the process complications are more.
In terms of the process side of things, well, again, these are things that we are still kind of embarking on and working with our customers. So again, happy to follow up more with you. We have some specialists from a hydraulic perspective that again we can tie in with you there from if it's something you want to specifically look at and discuss. That's no problem. We can do that.
Yeah, and the last question is related to the impurities in the upstream section. I mean, the gas absorption after that it is coming. So there are possibilities of amine carryovers. Okay. So how you are addressing in case of supercritical situations?
Yeah. Again, it's quite critical for us. So again, we can take that question away. We can look at that on an individual basis if that's okay. Thanks.
Okay. Thank you.
Thank you. Good. Thank you. Okay. Oh, more questions?
On behalf of everyone.
I think that is all we have time for now, but if there are any follow-up questions, we'll be here at the end. If there's anything that you want to come and discuss, please do, and we can take that away and follow up with that. So thank you very much.
On behalf of everyone here, I would like to extend a sincere thanks to Mrs. Vijay Menon, Mr. Scott McAllister, and Mr. Gauri Shankar for sharing their immense expertise with us today. We are grateful to all of you for your time and for helping us navigate the future of global energy landscape. A warm round of applause for our distinguished speakers, please. Now it's time to felicitate our distinguished speakers of the session. Before felicitating the speakers, I request our ex-president, Mr. Rajaganapati, Senior Engineering Rotating Equipment KNPC, and Mr. P.P. Muthu, Operations Manager, Golden Palm, to the stage, please. I invite our speakers, Mrs. Vijay Menon, Mr. Scott, Mr. Gauri Shankar, to the stage. I also request our President, Mr. Rajendra Kannan, and our General Secretary, Mr. Stanley, to accompany them. I would like to invite Mr. Raja to felicitate Mrs. Vijay Menon with a shawl. Now I request our President, Mr. Rajendra Kannan, and our General Secretary, Mr. Stanley, to present the memento to Mrs. Vijay Menon. I would like to invite Mr. P.P. Muthu to felicitate Mr. Scott with a shawl. I wish to invite Mr. Raja to felicitate Mr. Scott with a garland. Please allow me to invite Mr. President and our General Secretary to present Mr. Scott with a memento. I invite Mr. Raja to felicitate Mr. Gauri Shankar with a shawl. May I invite Mr. P.P. Muthu to felicitate Mr. Gauri Shankar with a garland. I would like to invite our President and the General Secretary to present Mr. Gauri Shankar with a memento. Thank you, everyone. Following the first session, we move on to our second technical presentation of the day, titled Pumps Aftermarket, that is pump upgrades, re-rates and field experience. This session will be presented by Mr. Callum Scott and Mr. Sanjit Das, Regional Sales Manager, Pumps AM from Celeros Flow Technology. The discussion will focus on aftermarket solutions aimed at enhancing pump performance and extending equipment life. Participants will gain practical insights into the upgrade and re-rate strategies supported by real-world experience and reference cases, offering guidance for improving reliability, efficiency, and operational flexibility of the existing pump systems. Let me take a moment to introduce our speakers, Mr. Callum Scott and Mr. Sanjit Das. It's my privilege to introduce our main speaker, Mr. Callum Scott, the pump upgrades and re-rates techno-commercial lead at Celeros Flow Technology. His extensive career spans critical roles in hydraulic design and aftermarket engineering, having served as a senior hydraulic design engineer at Weir Pump Limited and chief engineer at Argyle GTOs Limited. Currently based in Abu Dhabi, Mr. Callum is responsible for leading complex upgrades, re-rates and re-engineering projects within the pump aftermarket sector. His deep technical knowledge in pump optimization and lean manufacturing has made him a leading authority in enhancing industrial efficiency across the Middle East. We are honored to have a distinguished expert share his insights on advanced pump technologies. It is also my privilege to introduce our next speaker, Mr. Sanjit Das, a distinguished engineering professional with nearly 2 decades of experience in design and management of complex pumping systems. Mr. Das currently serves as a project manager at Celeros Flow Technology in Noida, India, where he leads high-stakes engineering initiatives for some of the world's most demanding industrial environments. Mr. Das' career is marked by deep technical versatility. He has spent over 14 years with the organization, progressing through critical roles, including assistant manager of aftermarket engineering and lead engineer for brownfield projects. His expertise lies in the intricate balance of maintaining and modernizing existing infrastructure, ensuring that legacy systems meet modern performance and safety standards. With an engineering degree from Nagpur University, he combines a rigorous academic background with extensive hands-on experience in global project execution. Please join me in welcoming the experts in engineering resilience and lifecycle management, Mr. Sanjit Das and Mr. Callum Scott.
Okay.
Pardon. Who's you got there? No. Hey, wanna come? That's only one word. No, but thank you very much. I've been impressed the moment we came in tonight to set up, Sanjit and I, and Gowrie, Scott, VJ, Khaled. And the speeches, you know, very inspiring, and it was a word in your mission statement on engineering, so I'm very, very impressed with the Tamil Nadu Engineering Forum. So hopefully tonight, and I think it was very inspiring what Scott and Gowrie took us through with regards to very high technology, leading edge technology that we're doing at Celeros Clyde Union Pumps. What Sanjit and I tonight will be talking about is, hold on, just on the aftermarket, which is after Scott and Gowrie's put the new equipment out to site. You know, Sanjit and I support here in Kuwait the likes of KLC, KNPC, KOTC, that sort of thing, is on the brownfield sites where pumps have been on site for maybe 10, 20, 30, even 40 or 50 years. So we'll be talking tonight on the upgrades, re-rates, retrofits and the re-engineering. Now this applies to our pumps, but also applies to any pump, centrifugal pumps. And our sort of legacies go way, way back, decades, working on any pump. So any pump problems that are in the brownfield and refineries, power stations, we can apply our engineering solutions. So this is what we're here to talk to you tonight on our engineering solutions. So why upgrade, re-rate? Basically, we're a life cycle partner to pump end users. We deal a lot with the pump end users, the likes of KOC, KOTC and KNPC. So we deal with them all the time. We've supplied pumps to them way, way back. And this is what we're all about. We are here to reduce the life cycle cost of owning and operating a pump, and by applying our engineering solutions to these pumps. I'm struggling. Okay. So what we're going to talk to tonight is just our qualifications, what makes us qualified to do all this engineering on our own pumps or somebody else's pumps. We'll describe what an upgrade is, a re-rate is, what a retrofit is, and what re-engineering is, and why they need to apply these engineering solutions, when to carry out these engineering solutions, and the techniques that we use, and then case studies. You know, we're not just here to make some promises and talk about it. We've been delivering this for decades. All these engineering solutions. And then lastly, we'll just talk about our facility in Abu Dhabi. So this is it. So it's just encapsulated, we call it engineering solutions. VJ mentioned it earlier in the evening when VJ kicked it off, how old our company is, 82. And these were the first sort of pumps that we started building. Mostly boiler feed pumps. These are direct acting boiler feed pumps driven by steam chest at the bottom, and then the pump here at the top. So these are double acting, some are single acting. It was called a simplex pump. But these were all built in Cathcart, Glasgow. Scott McAllister, Scott who talked tonight, Scott's based back at Cathcart. That's where I started my career as an apprentice, and that's George and James Weir. So they were the two brothers that started it all off in Glasgow. Now, in 1910, I'm going to talk a wee bit about history. Gowrie and Scott talked a lot about high technology.
I'm going to take you right back to very, very old technology. But back in 1910, Glasgow Weir Pumps supplied some pumps to Harland and Wolff in Belfast in Northern Ireland. So what, you're asking? Well, back in 1910, they built a ship called the RMS Titanic. That's a Royal Mail ship, the Titanic. And it was launched on May 11th, 1911 in Belfast. And it was us that supplied the pumps for the Titanic. That's her leaving Queenstown in Ireland. That's probably the last photograph of the Titanic. But these are the actual pumps that were fitted to the Titanic. The Weir pumps, the boiler feed pumps, the double acting feed pumps. And that's an actual photo from the records at Harland and Wolff. So anyway, as everybody knows, sadly the Titanic ran into an iceberg on her maiden voyage on the 14th in the evening 1912 after hitting an iceberg and sank just under 3 hours. She broke her back on the engine room, so when it sank on the seabed, a lot of the engine room equipment was spread all over for the seabed. So the bad news in that was that over 1,500 people were drowned. The good news, it wasn't our pumps that caused the problem. They were still running when she sank, and this man gets the blame, Captain Edward John Smith. He ignored the warning. He didn't have a safety moment that morning in the bridge, sadly enough. And he ignored the warning, and it was full steam ahead. He wanted to break the blue ribbon record on the maiden voyage. So sadly enough, the Titanic was no longer. But anyway, that's a bit of our legacy. I just wanted to give you that. You're all engineers, and I know we all love engineering. So that's just a wee bit of history for you. So back to our other story on the upgrade re-rates. So what is an upgrade re-rate, retrofit, re-engineering? On this was a slide that Scott put up for us, and this is just our legacy in the Middle East. This is all our installed base in the Middle East. So we've got over 8,000 pumps in the Middle East. Aramco, KOC, Qatar Energy, KNPC, KOTC, PDO in Oman, ADNOC in Abu Dhabi. So we've got an awful lot of pumps. These range from BB3s, BB5s, BB1s, verticals, and the reset pumps, and also on the plenty pumps, the lube oil screw pumps. So this is us back just to explain what upgrade re-rates, retrofits, re-engineering is. On the left here you've got asset performance. This is where we can actually change the performance of an existing pump. That pump might have been on site for 20, 30, 40 years. We do a lot of this in the power stations where we can make the pumps more efficient, reduce the power. Also in oil and gas, nowadays the oil companies are wanting to produce more gas or oil, so we're getting asked to increase the pressures in our pumps, increase the flows in our pumps. Sometimes it's not our pumps that we get involved in. We work on other people's pumps. So we can change the performance, higher pressure, higher flow, lower flow. So we can customize an existing pump to suit another process duty. Also, we can enhance the pump efficiency. Some of these pumps were designed over 30, 40 years ago. Nowadays, Scott was highlighting all the computational tools that we use, so we can actually design these pumps maybe 2-3 points more efficient. Some of these boiler feed pumps, water injection pumps, are in megawatts, 10-12 megawatts. If you can increase the pump efficiency by 2-3%, that's a significant power saving in kilowatts, reductions in carbon emissions, but also money, saves an awful lot of money for the end user. So that's the asset performance, category A. Category B is asset reliability. This is more on the upgrades. So the first one's re-rates, this is upgrades, where we're actually improving the reliability of the pump, and that could be through improving the materials, changing the actual design configuration of the pump, maybe fitting improve seals, upgrading the mechanical seals, upgrading the bearings, shaft stiffness, that sort of thing. We do an awful lot of that. And then on the last one is asset availability. That's more on the condition monitoring side of it. So category A is more on the hydraulic design, the re-rates. Category B is like the mechanical design. We're applying our design on the mechanical aspects. And then the last one is more on the condition monitoring, the instrumentation, which is basically looking after the pump.
Yeah, so Karan, if you can go back please.
Right.
So here we are talking about these three categories. So category A, we are talking about here, like you are seeing a lot of cases like when the pump comes in new as a project. So everything depends on the process design. Now, right from the licensor to the EPC, so everyone keep on adding their, I'll say like buffer to the grid point, to the design limit. But actually what pump runs in the field, it depends on the system. So that's how the pump runs. So a lot of times we have seen the actually pumps designed on certain parameter, but those parameters are not required at site. So there comes the asset performance. So here we have seen a lot of cases like, you can improve the performance by reducing the flow or increasing. If it is required, you want to reduce the head, or if you want to increase the head. So those comes in this category. So that's why we call it an asset performance. Now reliability, like any industry, equipment has to be reliable. And end of the day, it is tied with the economics. If the equipment is not reliable, you cannot run any business. So that's how the reliability comes in the picture. So there are different programs or different solutions we can provide which makes the equipment reliable. And the last one is that it's like a continuous process. Once we are running an equipment, we need to monitor it continuously that we have the on-time availability as per the process requirement. So that's how the third category, which is the asset availability, comes in the picture. So that's how we have categorized all the upgrade rates which goes in the industry in these three categories.
Hey, thanks, Sanjay. Good. This thing takes a long time to change. Yeah, this is a good. Our pie chart is a good indicator here, just on the the life cycle cost, where the costs are, and you can see here most of the life cycle costs are in the energy, 55%. And the rest, the bulk again is in the maintenance. So it's 55% on the energy, and that's about 28% on maintenance. And you can see, a message for the EPCs and the people that are buying the new pumps on the projects. You're only talking about 5-8% as the initial cost of the pump. Once the EPCs are off the landscape, then it's up to KLC, KNPC to look after these pumps and try and reduce, try and keep the cost down of owning and operating the pump. And you can see it's a significant amount, over the 20 years, just based on an average. So re-rate, just on upgrade re-rates, Sanjit talked about their increased reliability, reduced power consumption, energy costs, reduced carbon footprint. 1 kilowatt hour is roughly about 0.5 kilograms carbon. And again, that's a significant amount when you're talking about megawatts, which a lot of the pumps that we work on are. And then also safety, if they are unreliable and you're pumping critical liquid.
And here, this regarding this energy cost, now it varies from country to country, region to region. So if you have any this kind of requirement, so we can calculate you complete payback depending on how much energy you are saving, considering that what is the cost of the energy in the country. So we can have a complete, I would say a calculation which will give you not only that how much you are investing in that upgrade or re-rate, what is the ROI for that investment. So we can have that kind of calculation, we can come up with that kind of proposal also.
Yeah, and one of the case studies that we'll show you tonight, there's quite a significant saving, and the payback period was only 12 months. Now, this is a bit of a school lesson in hydraulic design. Every day is a school day in engineering. We're always learning. Every day we learn something in our work in engineering. So a lot of you guys will probably know this if there's rotating equipment engineers in the house. Gary mentioned that earlier somebody had asked a question about varying the blades. Centrifugal pumps are only designed for one flow, one duty. So when they go out to the field, the EPCs have given us a duty, and this laser pointer's not working the best. So this green line here is given to us by the EPC or the end user. Here is a static head and then the dynamic head. So where it crosses here, we design the pump for that flow and for that head at a certain speed. And of course, based on the MPSH available, very, very important. So in a real world, the best efficiency point of the pump should correspond to the duty that the EPC or the end user has asked us to meet. But again, we don't live in a real world, and a lot of the times when the pumps go to site, or maybe after 20, 30 years, process conditions change, that type of thing, and the pump can operate off its best efficiency point. A lot of times what we see when we go to site and we're maybe we're investigating a bad actor, poor reliable pump, or the power station wants to reduce the power. A lot of times the operator doesn't actually know where he's operating the pumps with regards to best efficiency flow. And we can quickly highlight to them where they're running the pump by just doing an analysis based on the data available in the control room and down locally at the pump, or we can go to site and do a full-blooded performance test. But you can see here when these system resistance curves have changed, either the statics change, that could be the boiler pressure, or that could be tidal, and then the dynamic head changes. That could just be an aging pipe system. So there's quite a multitude of things that can cause that. And then as you can see, the pump will operate at this juncture to the left, or this juncture here to the right. And then you can see that the pumps are operating pretty far away from their design point. And that causes, again, that can cause a lot of problems. And here they are. These are just the sort of hotspots of problems that can cause. Somebody was asking before about if they can operate without spillback, with continuous recirculation. As Gowrie said, you can't really run in here at the low flow. API 610 stipulates that. They've got tight regulations on that. So starting at low flow, you're going to get very, very high temperature. You're going to get a lot of cavitation because it's fluid borne. There's a lot of recirculation, suction recirculation, and then as you come out to best efficiency point, things are sort of dying down, and you're getting a very smooth running pump. But then if you go beyond the best efficiency point to the right, you've got cavitation. You've got cavitation in here as well, suction. So you've got suction recirculation on the left, and then to the right, you have discharge recirculation. So the liquid can actually come out the discharge of the impeller, and then it can actually come back into the impeller, back into the suction. It's like a figure of 8, and that's what happens in discharge recirculation. So the reliability is very, very much dependent on the operator. This is a great graphic, and this was done by DuPont way back in the 70s, and they did a big analysis because they own thousands of pumps all over America in their refineries, and they did a big analysis on the costs of running their pumps. And lo and behold, what they discovered in their analysis was the lowest running cost for the pumps were the ones that they were running at the best efficiency point, and the ones that were costing them more money were running to the right and to the left of the best efficiency point. So when's the right time to re-rate? These are all the sort of red flags. Low mean time between failure. You know, as a minimum, you're looking at 48 months, but you know, you're looking at plus, what's that for 72 industry drives? Yeah, 72 months, yep. Change in operating conditions could drive it. You want a higher flow, lower flow, higher pressure, lower pressure. It could be high vibration, bad actor, poor mechanical seal performance. So that's some of the drivers. High bearing failures. And again, power stations, poor efficiency. So our techniques, I'll go through this because Sanjit and I have got a lot to go through tonight, so, and we don't want to take up too much of your time, and we've got a lot to show you. This is just some of the tools that we can use to change the performance of the pump. This is a D stage where we've actually taken out 2 stages of this multi-stage pump. It looks like a BB3, and then you can see here on the right the blue curve is the original duty and the red curve is the D-staged performance. We do this, we carry this out quite a lot, even in reservoirs in the oil and gas, because the reservoir profile can change over the years. And this can save a significant amount of energy. We've got a case study that's similar here that shows.
Yeah, so here another important thing is that it's not only destaging or restaging. So suppose if you need to change the head or the flow, like since you have seen, like we have a lot of other heritage brands, so we have a lot of hydraulics with us. So what we can do, we can check with our other hydraulics if we can fit in the existing envelope. So by that way also, by changing the hydraulics completely, maybe individual impeller or maybe complete hydraulics, we can change the duty point, like required duty point, whether it's a reduction in flow or increase, same for the head or the pressure.
Yeah. So this is just going over the cavitation side of the things, because it's really important that when you are running off peak. This is one on the suction, suffering from cavitation, and on here, yeah. So you've got suction, cavitation, but you've also got cavitation caused by the discharge, and that tends to happen on the trailing edge of the impeller. But on this one here, you'll see the suction phase cavitation, and this is because you're running at the lower flow. If you had discharge cavitation, you would probably see that on the back side of the impeller. And we were able to redesign a first stage impeller. Scott was asked a question earlier. We can redesign the impeller to reduce the MPSHR, and we do that on existing pumps. Again, I'll quickly go through this because there's a lot to show, but this is just some of the tools we can do to tweak the performance. This is underfiling. We've underfiled the blade. We can push the flow out slightly. This thing doesn't change. This is one that we've done on this is a trouser leg casing, and what we've done is we've cut back the cutwater. That opens out the throat area, so that allows more flow through the pump. It's taking a long time to change. So there you go, see we've pushed the best efficiency out to the right, by opening up the throat area. And this is here a void lip extension where we're actually closing the throat area. We've added a cutwater in here. It's quite a laborious job, it's quite a tricky job to do, but we've done it. This is taking a long time to change. I don't know if the batteries are done. So here just some of the photos and the drawings what we did. Again, it's a very, very intricate job, but we did it, I think that was maybe on a rewrite that Scott was involved in on the North Sea. Our factory and do a performance test and prove to the customer that the new duty, that we've met the new duty, so we'll carry out the test. You've seen the test shop that Scott showed earlier. We can do that in Ghaziabad in India. We've also got a test shop in India.
So for re-rate now, so there are two things to prove the performance, the committed performance. So one, we can do it at factory, like any other new pump. We can do the FAT of that re-rated pump, or we can do the SAT, which is basically site acceptance test. And depending on the customer requirement, we can do both, either of these two. So, but at the end of the day, through both of these FAT or SAT, we are going to prove that what are the duty parameter committed that pump is achieving at the end of the day.
Yep. For a re-rate or an upgrade, anything, all we would need, if it's our pump, that's great, we'll have most of the information. But if it's for a flow serve, Sulzer, whatever, KSB, we would ask you for certain data. Our own pumps, we would always ask you for the log data. We would look at all the log data. If it's a third-party pump, then we would ask you for a pump curve, pump data sheets, that type of thing. And then any service history, maintenance history, what's the future planned use of the pump, the criticality of the pump. So we would sit with you through a sort of information gathering process to get all the data for you. And obviously what the budget is, the cost is very, very important. Case studies, Sanjay's going to take you through some case studies, so I'll give you the doofer.
Okay, so this is for one of the case studies. This is really one of the interesting project we are doing. This is basically ADNOC, Das Island, offshore. So before I start, this particular pump was supplied in 1974. This is a boiler feed pump supplied from, in those days, the Glasgow facility. Pump is still running. There are total 6 pumps, 2 pumps are motor driven, balance 4 pumps are turbine driven, and customer want to extend the life for another 30 years. Because if you look at API 610, the design life is 25 years. When we supplied those pumps, that time API 610 was not there, but still pump ran almost for 50 years. And looking at the performance, customer want to increase it further. So what we did the complete analysis of the existing site condition. We got the complete parameter from the site. In fact, we visited the site just after COVID. We got the data, and then we have seen, because if you look at the design philosophy those days, in 70s, 80s, nowadays there are a lot of changes, a lot of, I will say, like upgrade in technology is there. And there are a lot of tools are also there, as like Scott and Callum mentioned earlier. So taking advantage of all these things, we are redesigning this pump. First of all, we are redesigning the lube oil system. Existing pump having the turbine-driven pump having the turbine shaft mount this lube oil pump. Now we are changing it to pump shaft mounted lube oil pump. Then we are also changing the mechanical seal design. The existing is a component seal. Nowadays that most of the cases component seal is completely obsolete. Either it has to be cartridge seal and it's a single, or must be double depending on the site requirement. So now we are changing this mechanical seal to the cartridge seal, which will give a more reliability of the equipment. The lube oil system also we are changing, and also we are changing the balance drum design. So that will give more stability to the equipment, not only the day-to-day operation, Also because, see, it's an offshore installation. So reliability has to be like, it's very, very important. So from that point of view, we are doing this upgrade, which not only will give another 30-year extension of the life, but also pump will be more reliable. There is some vibration issue at site, that also will be taken care by this kind of upgrade. And for this, another interesting thing is that, as I was saying earlier, that FAT or SAT for the upgrade jobs. Now, out of these 6 pumps, 2 pumps will go to Glasgow for FAT. So after we do the complete upgrade in our Abu Dhabi workshop, we'll send it 1 turbine-driven pump and 1 motor-driven pump to Glasgow for the FAT. So once FAT is successful, we'll bring back the pump and we'll install it. After that, again, we'll do the SAT. So in this case, we are doing both FAT and SAT to make it sure that we are going to deliver. By the way, there is no change in duty parameter. But main thing here is that the mechanical run, the stability of the equipment, the reliability of the equipment, that we are going to ensure through this FAT as well as the SAT. So this is another interesting job which we have done in those days. It was Qatar Petroleum, now Qatar Energy. So this is a vertical pump. We have changed this line shaft bearing material to the non-metallic. So you can see, like, again, the point is like what we are trying to say, it's not only the upgrade relay. At the end of the day, that should give you the benefit of the equipment reliability, the improved MTBF. So here you can see that the MTBF was earlier really, really low for any type of pump. 6 months is nothing in the industry. So after we did upgrade, each pump was running for 6 years plus, I would say. So that kind of benefit or advantage you can say here or there with the upgrades and redates, that kind of solution we are providing. So for the general upgrades, now this is another engine. It's basically a BPO. It's a back engine. It's basically a BPO. It's a back pull out for the OH2. So there are multiple benefits which we are offering through this solution. First of all, we can offer you this back pull out assembly. It's like a direct plug-in type of solution. There is no modification required at site. Suction discharge you are not touching. But the benefit is that you can change the mechanical seal again. Going back to the mechanical seal, 30 years back probably you used single seal or component seal. You want to change it to double mechanical seal, we can offer through this solution. You want to make it like more robust in terms of like bearings, we can offer the upgraded bearing in this. So in multiple front, right from your mechanical seal point of view, right from your operation point of view, you can say that with this back pull out upgrade, you can get another renewed life of the equipment. Now, another is that for the back pull out, like you will see like a lot of back actors are there in the equipment. There is a like basic thing. All the industry, all the operation, there will be some bad actor, more or less. So we can see those bad actors. We can find like what are the issues, and accordingly we can give you the solutions. And one of the solution for this OH2 pump can be a back pull out assembly upgrade. As I was saying that nowadays there is norm for the emission. So earlier that single mechanical seal, even double mechanical seal with Plan 52 was acceptable. But nowadays if you look at any new project spec, all the specs, most of the time if it is a liquid is hazardous, coming with Plan 53B minimum, because no emission is allowed. So in this case, back pull out assembly, as I was saying, that we can change the single seal to double seal, which will accommodate, which will have a bigger stuffing box, can accommodate that one. Along with that, whatever the mechanical sealing system you want, we can supply that also. And regarding that, the higher capacity bearing, so that not only it will have a more reliable equipment, you can, like any pump, depending on your operation, you are running, you are stopping, or maybe you are going from changeover from standby to running. So always there is a fluctuating load on the equipments. So if you look at that point of view, so we can upgrade the bearing design so that you'll have more robust equipment with you. Again, this we can improve on the other side for the back pull-out is the shaft design. We can give you higher diameter shaft, which will have a more better L&D ratio. In a way, it will have more reliability of the equipment. It can take more load. Like suppose sometime you are running the pump little far right side of the BEP or the duty point. So in those cases, the pump can take that load. So these are the features and benefit for the back pull-out. So right from, as I said, it will be a drop-in, plug-in solution. Don't have to do any modification. Take out the existing back pull-out, insert the supply the new back pull-out. Done. You can start the pump. Second is that, as I said, mechanical seal. We can upgrade the mechanical seal by this back pull-out assembly. Then we can have this bearing. We can improve the bearing design. We can add that cooling fan because. So now equipment is supplied. Initially as per the present process condition. Now, if any change in the process condition is there, whether in terms of change in the liquid characteristics itself, there is a change in the process condition itself, we have seen that it's taking toll on the pump. So in those cases, first thing is the metallurgy change, depending on situation. Second option is that we have different type of coating, which can give you a better life for the wet parts. So this is one of the solution which we have, like different type of coating we can offer you, depending on, again, it depends on the application, depends on the problem you are facing, depends on the process itself. So we have different type of solution for this. Any change in the process parameter, if you are facing any problem in terms of corrosion, erosion, we have a solution for that. So you can say this is one of the example. We have done this metal cladding. This is the first picture. You can see it's after 6 weeks operation. So you can see the condition. And definitely any hydraulic performance depend on the surface finish. So on the first picture you can see the condition of the surface. So after that we have given the solution of this metal, which performed well, and it's a cost-effective solution. On top of that, it is also giving the reliability of the equipment. So next one is the non-metallic items right from bearings, bearings. So there are different non-metallic upgrade we can do with the existing pump. Depending on your requirement, sometimes you need closer, tight clearance of the equipment to improve the efficiency. But the metallurgy doesn't allow it. So in those cases, we can offer you non-metallic items, non-metallic spares, which will allow for tighter clearance, improve the efficiency, improve the reliability, but also it will take out the risk of this. If it's a metallic one is there, all the risks it will take out. So this non-metallic solution can be done any type of pump. You can say whether it's a multi-stage pump, whether it's a back pull-out, whether it's a vertical pumps, depending on the requirement. It's not that one solution fits for everything. It's like a different solution is there for different type of. So this is just one table we have shown here, how the different non-metallic items, what is the range, what is the temperature, pressure it can take. You are quite aware, probably peak material, which is everyone knows in the industry. So in the peak also there are different types are there. So depending on the requirement, our engineering can select the material, and we can select that what solution is best for you. So coming to relate, now we discussed about upgrade, we discussed about the back pull out, and now we are coming to the relate. So relate is basically duty parameter. Now changing duty parameter can happen if you are changing the flow, if you want to change the pressure of the pump. Now that can come in the picture for various reasons. Probably you want more production, or there is a change in the upstream or downstream of the pump. There might be also some changes because of the process, because pump was installed 20-30 years back, and there are certain changes in the process. So because of various reasons, you may need to change the pump's duty. So that's what where that re-rate solution comes in the picture. So this is one of the case study we have done.